Thanks for joining us. I do see many names I'm familiar with, but also looks like we'll have some new guests actually for this webinar. Yeah, today it's a great pleasure to have Professor Igor Kadota with us. It's actually my first time meeting with Professor Igor too, I guess in this setting, more small group setting. The first time I heard about his work was actually in another workshop related to spectrum. It was a fantastic talk and also some of the good insight there. Yeah, so it's a great pleasure to have him with us today. Besides spectrum-related research, he has been at the forefront of studying next-generation wireless networks with a special focus on age of information or time-sensitive networks in general. So that's going to be the focus for today. He has been, as you can tell from his bio, fantastic researcher, has won many awards, best paper awards from the leading conferences such as InfoComm, YOP, and MobiHawk. And I guess when you were a student, you were a graduate student at MIT, you also won the mentoring award, right? Probably helping with the students there. Yeah. So Igor, so the floor is yours, please. Yeah.
Wait, thank you so much. Thank you all for attending. Thank you for the invitation. I'm happy and excited to be here. I'm gonna share my screen. Can you all see my screen now? Okay.
Yes.
Great. Thank you again. Thank you very much. I'm happy and excited to be here. Happy to talk about our project entitled WiSwarm, which is about wireless networking for a collaborative team of UAVs. But before I dive into the particular topic, I would like to invest a few moments into the bigger picture, right? So when you consider, future applications such as, search and rescue using drones, smart factories, telerobotic surgery, smart city intersections, and even many rural applications that I learned about during AraFest, a key part of those applications is that they rely on the existence of an underlying communication network that can support their performance needs, right? And, the performance needs of future applications are much more stringent and much more important than the performance needs of traditional older applications, such as sending and receiving email messages or voice over IP or even teleconferences, right? Because if the network crashes or if the network does not perform as well during this webinar, maybe you're going to be mildly annoyed because there's going to be some lags. However, if you're in a smart factory and the network does not perform as expected, your robots might get in the way of each other. There might be some major operational disruptions, and there might even be some safety hazards, right? So stakes are much greater here. However, our traditional networking solutions like 5G or Wi-Fi, they were designed for the previous type of applications, so sending and receiving emails and VoIP. So they are kind of like best effort designs and best effort implementations, right? So kind of my argument is that if we want to run our future applications, we need future types of networks that are customized to deliver the performance requirements of the application. Right? So the applications have those stringent performance requirements. So we need customized communication networks that can support those performance requirements, right? And of course, that we can talk about different types of applications, different types of large-scale time-sensitive applications. So we could talk about smart cities, smart factors, and whatnot. In this talk, we're going to focus on a specific type. We're going to talk about exploration of dynamic environments using a team of UAVs, and we're going to design this customized communication network for this particular application. So this is the application that you should have in mind throughout the talk. So we're going to consider this large-scale network of sensing drones. So we're going to have a few drones here. They have very low compute power. So they're basically just sensing the environment. And I have these dynamic environments. So basically what the drones are doing is they are taking video of the ground. And without any intelligent processing, they are just sending that video, those video frames, to the access points via this wireless communication channel. And the access point will forward that information with the edge server. And the edge server is going to aggregate information from all drones, and then the edge server will do some intelligent, considerations. Here it's going to monitor what's going on, identify, items of interest in these dynamic environments, and then control those drones, right? So the control of the drones is basically done by the edge server and needs to be communicated via the wireless access point again. So this is the scenario that we have, right? We have then this dynamic environment here, which is basically autonomous cars on the ground, and we have drones that are following the cars. Again, please remember that the drones, they don't do any computation, right? The drones just take images of the floor and send those images to our access point, which is here. So basically, the drones are taking images of the car, sending those images to the access point. The access point relays things to the edge server, and the edge server, sends back control information to allow the drones to, continue keeping track of the cars. So that's the application that we have in mind. We're going to model those drones as follows. So, here we have, a drone, and the drone is generating time-sensitive information, in particular generating those images with a rate lambda and placing those packets in a queue. And then this is an internal queue to the drone. And then the drone is sending those packets to the access points via the wireless channel, and the access point relays information to the edge server. So this is how we're going to model the network. And I'm going to use this model to introduce the concept of age of information. And then I'm going to formulate the problem of minimizing age of information in the wireless network. And to my knowledge, this was the first paper that actually proposed this problem of minimizing age of information in a wireless network with unreliable channels. And then I'm going to share with you some theoretical results. Specifically, I'm going to derive this lower bound on the achievable information freshness in the network. And then I'm also going to derive 2 scheduling policies with performance guarantees, right? And in this talk, we're going to focus on scheduling policies. However, in an actual network, packet generation at the drones, queuing discipline, and scheduling policies, they all matter for minimizing age. However, again, in the talk, I'm going to make some simplifications so that I can focus on scheduling policies. But if you're interested in the generalizations, I would encourage you to take a look at our paper or at our book, which also gives you a nice introduction to age and to this problem. But again, today we're going to focus on scheduling policies. And I'm going to discuss then implementations in the software-defined radio testbeds and in this drone testbed, right? So I'm going to start by introducing the concept of age of information using my simple model. So here again, you have a drone generating images and sending images to the edge server. And I would like you to consider this timeline here. So those time slots here, those are time slots. And the blue arrows, they represent time slots in which packets are generated at the drone. So when images are generated. And the orange arrows are the times or the time slots in which those images are delivered to the edge server, right? So here you have the number of time slots between generation and delivery. So this is the packet delay of the first packet. This is the packet delay of the second packet. And here you have the number of time slots between 2 consecutive packet deliveries. So this is the inter-delivery time. And again, inter-delivery time is like the reciprocal of throughput, right? So if you want to have high throughput in your network, basically what you're trying to do, you're trying to minimize inter-delivery time, right? So those are like old metrics that we are all familiar in the network setting. Today, I'd like to introduce a new metric, which is age of information. So we're going to capture how old is the information from the perspective of the edge server, right? Which, as you're going to see, is different from packet delay. So we're going to capture, again, how old is the information from the perspective of the destination. So here I'm going to plot age of information over time. And I would like you to consider this moment. So this is the moment in which the edge server received the first packet, right? So at this moment, the question is, how old is the information from the perspective of the edge server? So the edge server just received this fresh information, which was generated Z1 time slots ago. So the age of the information becomes Z1 time slots. And in this time interval here, the destination does not receive any new information, right? So any new packets. So the information at the server is just getting older and older and older. So the age of information increases over time. And then the edge server receives the second packet, and then the age information is updated to the packet delay, and then it increases over time. So here you see the figure that you always see in any age information paper of the sawtooth pattern. And what I would like to highlight here is that age information captures something new that cannot be captured just by latency or throughput, and also something meaningful, right? So if I tell you that at time t, the age information is 2 seconds, it means that from the perspective of the destination, the information that it contains, the freshest information that it has, is 2 seconds old, right? So if I want to have a server with fresh information about the position of the cars on the ground of my dynamic environments, what I want to have fresh information, which translates to minimizing the curve, the area under this curve, right? So that's going to be our goal. Now I'm going to share with you some, relationships between age information and position uncertainty. So consider the
Excuse
bird
me,
life.
Igor.
Yes.
It looks like it could be yeah. So if you may be able to close that,
Yeah, I tried. It's not.
That's blocking the rotation.
Yeah. I try include computer sound. I'm not really sure what that is. I'm trying to
Can
click
that
on
be
it.
moved around to the corner by any
Yeah,
chance?
no. I'm trying to move. Should I share, unshare and share again?
Yeah, maybe we can try that. Yeah.
Okay.
See if that would help.
Yeah, sorry about that. I saw
No,
that.
no, take your time. Want to see your full rotation. Awesome, great.
Maybe. Okay, maybe
Thank
that's
you. Yeah.
perfect. Thank you, Wei. Appreciate it.
Yeah,
If it
awesome.
appears again, I'm gonna try something. Okay. So this is age of information. And again, so again, this interdelivery time. So I for me is gonna be the interdelivery time of the first packet. Now I'm gonna share the relationship between age of information and position uncertainty. So I would like you to consider this bird eye view of my system, right? So here I have the cars, they're moving around, I have my access points, and from the perspective of the edge server, I'm gonna have this last known position information. So that's the last known position information of card 3. So card 3 is here now, but I'm the edge server, I don't know about this, right? I only know that the last known position of card 3 was here. And suppose that at time t prime, the age of information from the perspective of the edge server is 3 seconds. So, I have my information at the edge server, so this last known position information is 3 seconds old. That means that this car has been that has been moving around with an average velocity of W3, has been moving around for 3 seconds without the edge server knowing about it. So the position uncertainty associated with car 3 is going to be given by this radius here that is centered around the last known position and has a radius which is velocity of the car times age of information. So that's a very concrete example of like how age of information is related to a performance metric that the edge server really cares about, right? Because if the edge server would like to be able to control the drones to follow the cars, it must know where the cars are at all times. So this position uncertainty here has to be minimized. And that's going to be our objective function. So we're going to design a communication network that will attempt to minimize the position uncertainty of all cars in my network. So you're going to see that this is going to be my objective function, minimizing the sum of the velocities times age of information, right? So now I'm going to formulate the problem of minimizing age of information in my network. So again, I don't have one drone, right? I have n drones, and each drone is going to generate packets and place them in a queue, and each drone is going to have a priority or a weight. And in this case, for me, the weight is going to be the velocity of the car that this drone is tracking, right? But it can be something different. This weight could be related to the area in which the drone is, or it can be related to the cost of the drone. It can be whatever you want, but in my case, this is going to be the velocity of the car. And each drone is going to transmit packets to the access point using this wireless channel, and this wireless channel is unreliable. So every transmission from drone 1 has a probability P1 of being delivered successfully, and with probability 1 minus P1, there's going to be a transmission error. In addition, this wireless channel is also shared in the sense that there's only one frequency, so all drones are sharing the same resources, so only one drone can transmit packets to the access point at any given time slot. And as soon as the access point receives a packet from a drone, it will relay the image to the edge server, and then the age information associated with a particular drone would go down, right? Because you receive fresh information. And the edge server cares about the age information of all drones, not only one. So for simplicity, in the talk, I'm going to assume that sources or the drones generate fresh packets whenever they want to. So they can generate fresh images at will. This is a simplification, right? So if you go to my papers, you're going to see that I'm assuming that drones generate packets according to a binary process and put them in a queue or something. However, for the talk, because I want to focus on scheduling policies, I'm going to assume that sources or drones generate fresh packets at will, and this will simplify some of my equations and some of my proofs. As a result, the age information will evolve as follows. If a packet is delivered in time slot t, this packet was generated right before transmission. So the time between generation and delivery is going to be 1 slot. So the age information for every fresh packet is always going to be 1. And then whenever a packet is not delivered in time slot t, then age information just increases linearly, right? So this is how age information is going to evolve for me. But again, just a simplification for the talk. So, packet generations are going to be at will. So whenever a packet is delivered, age information goes to 1, right? As opposed to going to the packet delay. So my goal is going to be to find a transmission scheduling policy pi star that minimizes the expected weighted sum age of information, and I'm going to break this down. So this is the age of information at time t from drone I when I'm running scheduling policy pi. And I'm taking the expectation of the data information, I'm multiplying by the priority of the drone, I'm summing over all the drones, I'm summing over time, I'm taking the average, that's my expected weighted sum data information, and I'm taking the limit as the time horizon goes to infinity, and I'm trying to find a scheduling policy that minimizes this quantity. And if you take a close look at this is basically the time average position certainty. So basically what I'm trying to do here, I'm trying to develop a communication network that is customized to the application in the sense that it tries to minimize position certainty of my cars, right? And I'm running this optimization over the class of on all non-anticipative policies. So all policies that do not use future information in making decisions in the present. And I'm going to say that I'm going to develop a policy in this class, and an arbitrary policy is going to be called pi. So a few more words about what a scheduling policy is. So a scheduling decisions during slot T are basically going to choose different drones at every slot, right? So basically what happens is at the beginning of slot T, the access point is going to select one of the drones, and the selected drone is going to have this indicator function here, UIT equals 1, and all other drones are going to have indicator function 0 because they are not selected. So again, the access point selects only one drone. The selected drone is going to generate a fresh packet, transmit that packet to the access point, and that transmission will happen, will be successful with probability P, and with probability 1 minus P, there's going to be a transmission error. However, when the transmission is successful, then I have this other indicator function here, which we're going to use in future proofs. And this indicator function here, DIT, is going to be 1 when the packet is delivered to the access point at the end of slot T, and 0 if it's not delivered. So that's the scheduling policy, and that's what we're trying to optimize. We're basically trying to optimize, how to select drones in order to minimize position uncertainty, right? That's basically the goal. With that in mind, I'm going to share with you some theoretical results. So the goal is, to find the transmission scheduling policy pi that selects in every slot the optimal drone to get information from in order to minimize the expected weighted sum of information. And if you remember the expected weighted sum of information equation, right, I have this sum over time. And if you know dynamic programming, you're going to see that that's the first thing that you should try, right? They have the summation over time of the rewards, and it's perfectly suited for dynamic programming. So it's the first thing that I tried. And dynamic programming actually solves the problem. So dynamic programming computes the data information optimal policy. But the key word here is compute, because basically what dynamic programming does is at every given slot T, it considers all possible states and computes the expected future rewards of all decisions. And this is very high complexity because I have to consider the entire future and the future expected reward for all actions. So indeed, dynamic programming solves the problem. However, it's a very high complexity policy that the computational complexity grows exponentially with the number of drones in the network. So there's no hope of ever implementing this in a real system. And I saw that there was a question now about heterogeneity, and I'm going to get to that in my next slide. So this dynamic programming solves the problem for heterogeneous networks. However, it's a high complexity solution. So the next question that I had was related to the question. The next question that I had was, can I come up with a low complexity policy that is optimal for some kinds of networks? And the answer is yes. We came up with this greedy policy that is optimal whenever the network is symmetric, whenever all drones have the same weight, link qualities and the same weights, so everything else is symmetric. The only variable thing in your system is going to be data information, and in that case, the greedy policy is optimal. And the greedy policy works like this. At every given time slot T, I observe the data information of all drones, I select the drone with highest age, and I select that drone. And if that transmission is successful, my data information is reduced. So naturally, that's an obvious choice for a scheduling policy, and it's obviously data information optimal, but proving it is a little bit harder. So we use stochastic coupling to prove this result here in our paper. Excuse me. But now, maybe some of you are thinking this, symmetric networks are great for theoreticians, but they're not something that often happens in practice. So the next question became, can we generalize this result and come up with low complexity policies for general heterogeneous networks? And the answer is yes. However, obtaining the optimal data information policy for heterogeneous networks is still an open problem. So we came up with low complexity policies with performance guarantees. But to get performance guarantees, we actually need the benchmark, and our benchmark is going to be this lower bound. So I'm going to tell you how this lower bound works. So you tell me how your network is. You tell me how many drones you have, what are the weights or priorities of those drones, what are the quality of the links. And I'm going to use this very simple equation here. I'm going to plug in the numbers. I'm going to get the lower bounds. And I can guarantee you that there's no policy that can get a performance that is better than my lower bound. So there's no existing policy that can be better than this particular lower bound here. And I'm going to prove this lower bound in a few slides. And having the lower bound, I'm going to derive low complexity policies with performance guarantees. And this is what I mean by performance guarantee. So I'm going to give you a policy pi, and I'm going to say that my policy pi is beta optimal. So beta could be 2. My policy pi is 2 optimal. That means that the performance of my policy is never, for any network setting that you might cook up, it's never worse than beta times the lower bound. Of course, that my policy is never going to be better than the optimal, it's never going to be better than the lower bound, but it's never worse than beta times the lower bound, where beta is a constant. So I'm going to talk about those two results in the next slides. Before I can do that, before I can prove my lower bound, I need this lemma here, which looks at area information from a different perspective. So this is the weighted sum area information. So I have no, this is similar to my objective function, but I don't have the expectation here, right? So I would like to prove this equality here, which is an equality with probability 1. And to do that, actually, I just need to prove this result. If I can prove that the time average area information can be written this way, with probability 1, and I plug this into here, I can directly obtain that. However, before I can do any of this, I have to introduce some notation. In particular, I have to introduce this I and this M operator. So consider the timeline and consider one particular drone. Now consider the sequence of all packet deliveries for that particular drone. I is going to be the sequence of inter-delivery times. So basically, you're counting the number of time slots between 2 consecutive deliveries from the same drone, and you have this sequence of I's for variable M's, where M is the index of the packet. So now you have this sequence of inter-delivery times, and the operator M is a sample mean operator. So here you have the sample mean of the first of the inter-delivery times, and here you have the sample mean of the inter-delivery times squared. So my goal in the next slide is going to be to prove that the time average age information can be written this way. I'm going to give you some intuition of how that can be done. So consider this timeline here with 2 consecutive packet deliveries. Let's look at how the age information evolves. So after a packet delivery, age information goes to 1, and then it increases over time, and then it goes to 1. But notice that age information increases up to I. So it goes from 1, 2, 3, and I, where I is 4 here, and I here is going to be 3. So it always grows from 1 to I. So the sum of the age information between 2 consecutive packet deliveries is always 1 plus 2 plus 3 plus I. So this is an arithmetic progression, and it's easy to find a closed form expression for this. So this is the expression for the sum of age information between 2 consecutive packet deliveries. And this is close-ish to what I want to get. I want to get to the time average, right? But to go from here to there, we have to play some arithmetic tricks, which are common in queuing theory. And if we play those, small tricks, we can get this expression here. And the sample mean operator comes from the fact that you have this sum here over time. So this is not the sum over one period, but over all periods, right? So you have this sample mean operator here. And if you cancel this sample mean of the first moment of inter-delivery times with this, you're going to get this expression here. And we have this approximation because time is finite. But if we take the limit as time horizon goes to infinity, as t goes to infinity, then this becomes an equality with probability 1. And that's kind of like the intuition of how we got this result in our paper. So this proves this lemma, but it does not prove my lower bound. So next I'm going to go from the lemma to the theorem. And to do that, I'm going to apply Fatou's lemma to the non-negative sequence of weighted sum age information. So I have this non-negative sequence here of weighted sum age information. And I want to put the expectation inside of the limits. And to do that, I need Fatou's lemma. And then I'm going to use the generalized mean inequality to get this squared outside of the sample mean operator. And if I can get this squared outside of the sample mean operator, I can cancel those two. And since I'm talking about the lower bound, what I can do is I can minimize the right-hand side. So this is the expression that I'm going to end up with. I'm going to end up with a minimization over the expected inter-delivery times. And now, if you remember, minimizing inter-delivery times is the same as maximizing throughput. And this is something that we know how to do, right? So minimizing age is challenging, but maximizing throughput in such a simple network is easy. And we actually have a closed form solution for this. We know that the literature had a closed form solution for that. So we just plugged the optimal solution into the expression, and we got our lower bound. So if you think of what we did, right? We went from a challenging age information problem to a simpler throughput problem, and then we plug in the optimal solution, and that gave us our lower bound. So that's our universal lower bound in the sense that there's no policy that can achieve expected weighted sum area information, which is better than lower bound for any network setting that you might want. So now that we have our lower bound, I'm going to talk about different types of scheduling policies that has different types of performance guarantees, right? So basically, first, I'm going to use renewal theory to come up with the optimal stationary randomized policy, and I'm going to prove that this policy is too optimal. And then I'm going to use the optimization to come up with the max fit policy, and I'm going to show that this policy is also too optimal. And I'm not going to be able to cover bandits today, but we also did some work with bandits, and we showed that we can use a restless multi-arm bandit framework to come up with a Wheaton index policy, and this policy is 8 optimal. But again, I'm not going to cover this. If you're interested in bandits, like I know many people are, please let me know. We can also chat offline. So next, I'm going to go over to those 2 types of policies, starting with the randomized policy. So a randomized policy is a policy that is as simple as a policy could ever be. So in every slot T, the access point will select source I with probability mu I, and this probability is fixed. So I select mu I for all drones. So if I have 2 drones, mu1, mu2, it can be, I don't know, 1/3 and 2/3. I fix this, and this is fixed over time. So the scheduling probabilities are fixed now, right? And if the scheduling probability is fixed, now in any given slot, I have probability mu I of selecting drone I, and that drone, if selected, has a probability P of having its packet delivered. So this function here that indicates a packet delivery is a Bernoulli random variable with parameter scheduling probability times probability of a packet delivery. And this is true for all slots. So the number of time slots between 2 consecutive packet deliveries is a random variable with the same parameters. And then those are IID over time for any node I, any specific node I, for all of them, right? So this is how the stationary randomized policy works. And the sequence of packet deliveries from node I is going to be a renewal process. And for a similar reason, the sum of area information in between 2 consecutive packet deliveries is a renewal reward process. So notice this. Remember that the sum of area information between 2 consecutive packet deliveries is given by this function, right? And this function is only, and this expression here is only a function of the current period length, which says that this sum of area information between 2 consecutive packet deliveries is a renewal reward process. And if the sum is a renewal reward process, we can directly apply the elementary renewal theorem to the expected weighted sum area information to get this very clean and easy result, right? So this says that, the expected time average area information for any particular drone is going to be given by the expected reward, which is the sum of it, or in this case, cost, the expected cost, which is the sum of area information in the period divided by the period length. This is kind of like the density of the costs over that period. And luckily, the expected period length is easy to get because it's just expected, interdelivery time, which is a geometric random variable, so we can easily get the expected value of it. And the expected reward is also easy because it's a function of this geometric random variable, right? So we can also plug in this easy closed form expression. And if you plug those into this expression, we get the expected weighted sum area information of any randomized policy. So for any randomized policy that you might want, the expected weighted sum area information that you should expect is given by this, where the only decision variable that you have is mu, right? The only thing that you have to decide is like, what is the scheduling probabilities for all drones? Of course, that the natural question becomes, what is the optimal mu, right? So the optimal randomized policy is going to select mu's that minimize the objective function. And you can solve this optimization here with like a 1-line Cauchy-Schwarz inequality, which directly will give you the result that the optimal scheduling probabilities are proportional to the square roots of the priority of the drone divided by the quality of the channel. And if you plug in the optimal scheduling probability into your objective function, you're going to get this result. And so this is the best area information that a randomized policy could ever hope to get. Right? So with that, we're going to prove one of our main theorems, which is that for any given network configuration, the optimal randomized policy is too optimal. And we're going to prove this by inspection. Right? So here I'm just copy pasting the expected weighted sum area information from the optimal randomized policy. And here I'm just copy pasting my lower bound. If you compare them, they're the same thing. Right? So the only difference is that I have this factor of 2 and I have this positive constant. So if you multiply your lower bound by 2, you're going to get this plus a positive constant, which directly proves that the performance of my randomized policy is better than 2 times the lower bound, because I have this positive constant here. So by inspection, we showed that the performance of the optimal randomized policy is 2 optimal. Right? So it's between the lower bound and 2 times the lower bound. And actually, when we obtained this result, we were quite happy, but a little bit cautious, because the age information problem is super challenging, right? Obtaining the optimal age information for a general network is quite a challenging problem, still an open problem. And we obtain 2 optimality, which is very close to optimality. Right? Optimality is 1. If you get a factor of 1 here, you're done. You get the optimal policy. We got 2 optimality. We got 2 optimality. However, remember that the class of randomized policies are very simple. They don't even take into account the value of age information over time. They only select, drones based on fixed probabilities. And by only adjusting those probabilities, we can get 2 optimality. Right? We're surprised, but of course, happy with the result. Now, key facts here is that the stationary randomized policies, they do not even take into account the value of age to do this scheduling decisions. So are there policies that take into account the value of age? And naturally, those policies should be better than stationary randomized policies. So to pursue this line of research, we thought about using max weight policies. But to talk about max weight policies, I have to quickly introduce Lyapunov functions and Lyapunov drifts. So I'm going to do a 10-second intro to a very important and deep subject. So Lyapunov functions are scalar functions that have a value that by design have a value that is small whenever your system is in a good state, and a very large value whenever your system is in a poor state. So here we designed this Lyapunov function here, which is the weighted sum of age information. Notice that if one or more drones have a very high age, the Lyapunov function is going to be large, and gamma here is just a positive constant. And the Lyapunov function is only going to be small when all drones have small age. Right? So this Lyapunov function, again, has a large value whenever your system is in a bad state. And the Lyapunov drift is defined as the expected 1 slot increase in the Lyapunov function. And the max weight policy is going to be designed to minimize the drift at every given slot t. So the max weight policy is going to try to minimize the drift. And by minimizing the drift, it's trying to contain the growth of the Lyapunov function. So it's trying to keep the system is in a good state with like low Lyapunov function value, right? So that's the intuition. And once you get the intuition, the rest is more simple algebra. We just plugged in the evolution of age of information. So this is how the age of information evolves. We plug this into the Lyapunov function. We plug in the Lyapunov function to the drift, did some algebra, and obtained this very nice closed form expression for the Lyapunov drift. Usually in the literature, you see bounds on the drift. Here, we actually have a closed form expression for the drift without any bounding. And the goal of the max weight policy, again, is to minimize this at every given slot t, but this is a constant. So the max weight policy cannot not do anything about this, so we can just forget about this term. The max weight policy is going to try to minimize this, which is equivalent to maximizing the sum. And to maximize the sum, the max weight policy is going to try to select one of the drones, and that drone is going to have UIT equals 1, and all other drones are going to have UIT equals 0, because only the selected drone has a 1 here. So to maximize the sum, what the max weight policy is going to do is going to pick the drone with highest value of this index. So it's going to compute the index, gamma times age times p for all drones, select the drone with highest index, and get a packet from that drone. So that's how the max weight policy works, and that's how the max weight policy minimizes the drift. Now we're going to prove our theorem. For any given network configuration, the max weight policy with this particular hyperparameter here is 2 optimal. And this hyperparameter here has a connection with randomized policies. You're going to see why. But before I tell you why, I would like to plug this gamma into my max weight policy here and show that this makes a lot of sense. So basically what the max weight policy is doing is this. At every given slot t, I want to select drones with high priority, good channel quality, and high age information. This makes a lot of sense, right? And one might even wonder, we didn't have to do all this fancy math with Lyapunov optimization to come up with this. One might be able to come up with this without all the fancy math. That's true. However, without all the fancy math, we would not be able to get this theorem, right? That shows that the max weight policy, the performance of the max weight policy for any network configuration is never worse than 2 times the lower bound. So we're going to prove this result next. So the max weight policy minimizes the drift, right? So the drift of the max weight policy is minimal, and any other policy does not minimize the drift. So the drift of other policies are going to be greater than the drift of the max weights. And we have closed form expressions for the drift. So we just plug them there. And we substitute this particular hyperparameter here, which relates max weight with randomize. And here you see the connection. And then by doing that, we can show that the performance of the max weight is always better than the performance of the best randomized policy. And we know that the best randomized policy is too optimal, therefore max weight is too optimal. So we prove this indirectly, right? We prove that max weight is better than randomized, and randomized is too optimal, therefore max weight is too optimal. And this result, again, it should be intuitive, right? Because max weight actually uses the value of age to make scheduling decisions, and randomized policies don't. So they should be better. But again, intuition and actually proving it is a little bit different. So we actually prove that this is true, and max weight policies are too optimal for any given network configuration or parameters that you have. So this is the summary of our theoretical results. We talked about greedy policies. We showed that they are optimal when the network is symmetric. We talked about randomized policies. We showed that they are too optimal. And we talked about max weight policies. And we also proved that they are too optimal. However, when we simulate those policies, we see that max weight is actually close to optimal. It's close to the lower bound because we have two bounds here, right? So that's my performance of my policy. And I have a bound which is lower bound or 2 times the lower bound. We show that for randomized, this bound here is tight. And for max weight, this bound and this bound here are tight. So max weight is very close to the optimal policy. I'm not claiming that is the optimal policy, but in simulations, it's close to optimal. So when we decide to deploy something in our drone network, we went with age-based max weight policy. Notice that when the network is symmetric, Ws and Ps are the same for all drones, and max weights degenerates into greedy. So in that case, max weight is actually optimal. But when the network is heterogeneous, then we can only rely on simulation results. But we can also rely on the performance guarantees, right? So this is always true, independent of simulations. So next, I'm going to completely shift gears. I'm going to only talk about system implementation and experiments. Yeah, I think there was a question about hardness of the results. Maybe we can address that later. I did not get a chance to fully read it. Usually we do.
We can come back. Yes. Yeah.
Back? Okay.
Yeah, we can come back to the questions. Yes.
Good.
Yeah. Thanks for the question too.
Yeah, thank you. Please keep them coming. I'm happy to answer any question that you might have. So we're going to talk about system implementation in this software-defined radio testbed and using drones and flight tests. So before I talk specifically about Wi-Fresh, which is our solution, I'm going to talk about Wi-Fi and how it would run such a system, right? So if we are using Wi-Fi to run the system, we're going to have multiple drones, and they're generating images, placing those images in a first come first served queue that is inside the drone, and then using random access, in particular CSM-ACA, to send packets to the access point. And those drones, as per Wi-Fi procedures, right, they would send information whenever they have it, right? If they have information, they try to send it. And if 2 or more drones transmit at the same time, there's going to be a packet collision, and that packet collision is going to be resolved using CSM-ACA procedures like backoff. But the point is, if you scale this system, you're going to have more collisions, which will lead to a lower successful transmission rate per drone, which will make your backlog in your queue increase, which will result in whenever you transmit something, that something is going to be old because it has been waiting for a long time in your queue. So you're going to have a lot of collisions, and whenever you have a successful transmission, that packet is going to be old because it has been waiting around in your queue for a while. So the ad server, as a result, will get stale information about where the cars are, which will lead to poor control of the movement of the drones. And you're going to see this in some flight tests. And how did we address this? First, we changed from first come, first served to last come, first served. So whenever image is generated, place that image at the front of the queue. Everything that is older, put it in the back, you can drop it, but don't transmit things that are older, transmit the freshest image possible. And instead of random access, we are doing scheduled access. We are using max weight to select drones. That way we don't have collisions, and in that way we can prioritize the correct drones, as opposed to having them transmit whenever they have information. Right, so that's our solution. And I'm going to kind of show how that works in practice. So the access points is going to run max weight policy, send a polling packet to the selected drone, and also broadcast trajectory updates to all drones so they can move around, right? Then the pod source is going to fetch data from its last come first served queue. So it's going to fetch its freshest data and transmit that image to the access points, which will then relay the information to the edge server. And the edge server and the access points, they're going to update their belief about the network states and about the environment. And this is something that I hid from you in my theory part. So the access point and the edge server, they actually do not know age information and quality of the channel. They have to estimate those things. And of course that, in the theory, I assumed that this was known and fixed, like P, right, was known and fixed. Here, I know that this is time varying, so I have to estimate it. And the way that I estimate P, for example, is, remember that access point is polling drones. So if in the last seconds, I polled this particular drone 10 times, and 5 of those times I received correctly a packet, that means that P can be estimated to be half, right? So that's how I'm estimating P over time. And then the access point is going to use those estimations to compute the indexes for all drones, select the drone with highest index, and then send a polling packet to that particular drone and get an image back, and so on and so forth, right? Meanwhile, the access point is also broadcasting at every cycle trajectory updates to all drones so that they can move and track the cars. So I implemented this particular system in 2 testbeds. And when I say I implemented, I mean a lot of students and faculty, right? This was a huge effort. It was like maybe around 2 years of effort. We had like 5, 6 students. We have multiple faculty involved. So it definitely takes a village. It's like a lot of different co-authors and collaborators that I have to acknowledge here. And some of them are here in the papers. Yeah. And we implemented this in 2 different types of testbeds. One in which we have SDRs. The other one where we had Raspberry Pis. So in the SDR testbed, we had access to everything. So SDRs are open boxes that you can actually go in and change the MAC layer using FPGAs. So we had FPGAs in those radios. So we actually went in and implemented less come first serve queue in the FPGA, and also MAC switch policy at the FPGA running in microseconds, right? So we implemented this at the MAC layer to get full performance, right? However, if you implement something like this and you talk to system researchers or people from industry, they are basically going to say, yeah, we're not going to change our system to implement your solution. Can you come up with something that has a lower barrier to adoption? And that's kind of like what we targeted here. So here we have Raspberry Pis and drones, routers that were bought from stores. We did not touch MAC layer or physical layer. All the parameters came from the box, right? We didn't touch anything here. The only thing that the student did was the student implemented in Python a middleware that would sit between the packet generation and TCP or UDP. So just a middleware, a Python packet that was installed at the Raspberry Pis and at the server to drive the Wi-Fi network to behave similarly to WiSwarm. So again, we did not touch Wi-Fi. It's still a Wi-Fi network, but we created this middleware that would drive the network to behave as close as possible to this one. Of course, we lost performance, right? So if you have 5 sources generating packets in this particular network with SDRs, you're going to have an age information for less than 10 milliseconds. I'm going to show a video of this. If you implement this and you have 5 drones flying around, you're going to have age information of less than 100 milliseconds. So we have a 10-fold degradation of performance, but as you're going to see, this is much better than what you would get with just Wi-Fi, right? So some implementation challenges, complexity was a big one. We had to implement things at the FPGA level, so it was very complicated. Going from theory to practice, right? We assume many things in our theory. We had to deal with them in our system implementation, like clock synchronization, estimation of parameters, packet fragmentation, right? We have an image. We cannot transmit an image in a slot, right? We have to fragment how to deal with that. Barrier to adoption was a big one too. It was hard to come up with WiSwarm and come up with this middleware that was implemented in Python that could drive the Wi-Fi network to behave as we wanted it to. Now I'm going to go over some measurements. So we considered 10 software-defined radios generating small packets with frequency lambda, which is variable. Of course, that we are more interested in the scenario where we have a lot of packets to generate. You have many nodes and you have a lot of packets, right? And we're going to measure the expected weighted sum age information for 4 different protocols. I would like you to consider those 2. So, Northwestern purple is like Wi-Fresh, and standard Wi-Fi is blue. The rest I'm going to explain a little bit later. And each experiment takes 10 minutes. So we are measuring the age information in milliseconds. So, this is like 10 seconds, right? Over lambda, where lambda is the packet generation rate. So we are more interested here, where we have a lot of packets being generated and transmitted. And if you measure the performance of Wi-Fi, you're going to have an age information of around 5 seconds. if you measure Y-fresh, you're going to have an age information of around 10 milliseconds, which is what we got with SDRs, right? So that's like 600 times improvement. And just to put this in context of the position certainty, if you have cars moving with a velocity of like 1 meter per second, this means a position certainty of 5 meters, only for cars that are moving very slowly. And with our Y-fresh system, we'll get a position certainty of 1 centimeter. So I'm going to show how this works in like a video. So we have here the SDRs, the base station making the scheduling decisions. And here you have, age information versus time. And I'm plotting here age information of the 10 sources, one on top of the other. And here you have like 20 milliseconds, 10 milliseconds here, right? So you can see there's around 10 milliseconds, the age information. But if you run, again, if you just run standard Wi-Fi, same network, same everything, you just turn off Y-fresh and turn on Wi-Fi. That's the age information that you get. So one of the sources is getting like 14 seconds age information, the other one is getting a 7-second age information, and a bunch of them are getting like 1, 2, 3, 4 seconds age information. And on average, you're going to get a 5 seconds age information here. Yeah. So I'm almost at the end, so I'm not gonna bother by this small thing. So here are the measurements again, and maybe you wonder, I had a 600 times improvement on performance. How much of this was because of the queue? How much of this was because of the scheduling decision? So if you have Wi-Fi and you just change from first come first serve queue to last come first serve queue, so still random access, you get an 85 times improvement. If you change from random access to polling, to max weight, you get a 7 times improvement. And maybe you're thinking 7 is not that good, but that's only because I said 85 times before, right? But 7 times improvement is almost an order of magnitude just because of scheduling. So that's also significant improvement. And notice that Y-fresh is the only one in which a higher lambda always leads to better performance. So if you think intuitively, right, if you want freshness and if you have a bunch of sensors, the more data that they generate, the better should be your performance. And that only happens if you have something like Y-fresh. If you have something like Wi-Fi and you generate too much data, you're going to have worse and worse performance in terms of freshness. So here I'm shifting completely to the drone testbed now, so flight tests. So here I have 2 drones following 2 cars. So here you have a bird eye view of like the UAVs are in blue, the cars are in red, and you can see that they track. Here's age information from 0 to 1 second. This mean tracking error from 0 meters to 3 meters. You can see that it follows. Okay, and remember that the difference between WiSwarm and WiFresh is a Python app. If you delete the Python app, this is what happens. So drones follow the cars the tracking is much worse. Age information gets significantly worse, and you have a tracking error that fluctuates a lot, getting very poor sometimes, right? And again, the difference between those two is only an app, a Python app. And we tried to scale the system up and fly more drones with Wi-Fi. Truthfully, we could not. 2 was the best that we could do. If you take a look at our papers, for 3, 4, 5 drones in Wi-Fi, we just left it blank because we were risking crashing drones. But we were able to run the system with like 5 drones for WiSwarm. And here you can see that they track the cars okay. And age information is of course higher because you're sharing the resources with more drones, but mean tracking error is still okay because you're able to prioritize the correct drones. And so those are our flight tests. And importantly, I'm not cherry picking here, and this was like one of the typical experiments that we had there. And again, finally, this is the outline of our work. We discussed a lot of theory, and then we went ahead and implemented our systems and showed that they actually work in practice. And just like one last slide on like the type of research that we do at Northwestern, in our research group, we try to consider like future applications like you saw. Then we use rigorous theory to prove theorems and get bounds on our performance on our algorithms. And then we implemented them using multi-agent like drones, photoplex chips, software-defined radios. Hongwei was talking about spectrum sharing. That's a big thing in my research group right now as well. And we're trying to use software-defined radios to implement algorithms in that area as well. So thank you very much for your time and attention. Again, thank you for the invitation, and I'm happy to take any questions.
Thanks, Igor. So maybe we can go to the audience question. Jay, when you look at the question, or you're like me, just pay for it. We can we unmute? Actually, maybe that's easier. Maybe folks can even just speak that. But do send question in. But yeah, Maybe Igor, we can look at Shauna has, yeah, Shauna is actually my colleague here. Thanks for joining us.
Yeah, so the question from Shannon was, are all the drones here homogeneous except their information weights, the Ws? Also, how is the dynamic physics of drone playing a role here? Yeah, instead of drones, can this be any agent sending packets? So great questions. So, you know, I hinted at the answer here during the talk too, right? So for greedy, we assumed that everything was homogeneous, including the weights and you know, link qualities. But for other policies, we did not assume that. We assumed that the network was heterogeneous. Dynamics and physics, this is a fantastic question. You know, in the theory part, we assumed that lots of the dynamics were, you know, that there were not a lot of dynamics. The only dynamic thing in the theory was the aid information evolution, right? However, when going from theory to systems, we definitely had to, you know, take all of the dynamics into account. For example, when, you know, computing the weights, we don't know the average velocity of the cars in reality, right? So we had to compute it or estimate it. So we had to know the velocity of the drone, you know, take consecutive frames of the drone and see how the car is moving, and then use like relative velocities to estimate the velocity of the cars, to plug that into our estimator, right? So dynamics played a huge role in the implementation part of the work. And instead of drones, can this be any agent sending packets? And yes, I'm currently thinking of like robots in a smart factory setting. And you know, it's very similar communication protocols could easily work there.
Thank
and
you.
instead of Wi-Fi, this could be 5G, and that's also something that I'm working on, implementing this in 5G.
Thank you, Igor.
Pleasure.
So my second question was regarding, since you're focusing on approximate optimality, right? Have you looked at the NP hardness or NP completeness of these problems, or is it known to be hard? Is that why you are navigating towards an approximate optimality sort of algorithms?
Yeah, you know, so, you know, I'm not sure of any like, okay, what I know is this: when we try dynamic programming there, we have a, I don't know if in the paper or the book, but we have a result there that shows that the complexity of dynamic programming is going to be exponential in the number of nodes. If you have a lot of drones, you know, computing the optimal choice, the optimal action at every given time of t, is going to be, the complexity of that operation is going to be exponential on the number of nodes. So, and that's kind of like what motivated us to go for low complexity solutions, right? So if you have a very powerful FPGA or GPU in your nodes and in your access points, and you can make dynamic programming work, fantastic, you get the optimal solution. But if you don't, then you need to go for some, you know, low complexity solution.
Thank you very much.
Of course, yeah. Pleasure. Thank you for the great question.
Of course.
Yeah, maybe if I may just add a note, maybe Shauna here, I guess we know for sure, I think I have not paid a close attention to this part, but I think in the multi-cell setting, this problem has been shown to be NP hard. What I'm not quite sure is single cell setting, maybe as Igor mentioned, since it's, you know, based on it could be, I guess.
I don't know, it's still an open problem. Yeah, I'm sorry, Shauna, go ahead.
Yeah.
No, like, you know, it's not a formal proof, but somewhat it looks like a knapsack, right? You're putting in a, you know, a bunch of things, right? You have to ensure that it is not crossing a certain budget, right? Which is your worst case. Like if you're the lower bound, right? So maybe it is hard. Yeah. No, I was just curious. Thanks for that.
No, this is a great point. You know, what I do know is that one, again, is an open problem, right? So if someone has an idea there, we also tried bandits, which you know, in theory could give us an asymptotically optimal solution.
So when you move to the bandit setting, is it like, you know, this sort of life of this information? Is that what is bringing in the dynamicity? Which
Yes.
Okay.
That's why it's a restless bandit, right?
Restless
Because the age information increases, right?
Right. Okay. Good to know. Thanks.
Perfect. Of course. Pleasure.
Hey, good afternoon, Arash. Thanks for joining us from Austria. So I guess your question, yeah, I think Igor, there's a question about the table on slide 15. The question is, how did you do the simulation Well, Jay or Ali, I don't know if you are able to unmute and Arash. Maybe he can
I am
even. We
already
can.
on.
Oh,
Hello,
okay,
everyone.
good. Awesome. Thank you.
This was which slide again?
Hello, everyone. Like, thank you.
Yeah.
Maybe I just, in general, can ask my question. You have shown some approaches, then you have shown some simulations that you said, okay, you have done some simulations, and then you switch to the practical perspective.
Yes.
Exactly. I was first interested to see how you have done this simulation, and like for me, it is super interesting to see how you have compared the result of the simulations with the practical work that you have done with the SDRs. Do they merge to each other? Did you compare them or not? Like, how did you do these simulations?
Yeah, fantastic. Thank you for the question. This was also a concern of mine. So simulations here were done in MATLAB. This is me just doing like some easy coding, simulate some event-driven like network that would have slots, and then at every given slot, I would select one of the drones or one of the agents to transmit, right? And get a packet with probability P and with probability 1 minus P an error, right? So very easy simulations. So, and in those simulations that I'm showing here, I'm not comparing them with the practical system. However, I have one paper, which is, I think, this, Infocom 21, that I exactly motivated by your question. I did exactly what you mentioned. In this Infocom paper, we do 8 information optimization for CSM-ACA. And then I compare my MATLAB simulations with actual measurements with this testbed, and I show that they match. Of course, there is some deviation, right? But I showed that in that paper that they match.
Yeah, and good, thank you. And my next question, basically, I think you mentioned that like in Austria we have some test beds, and we are doing like it's 4 or 5 years we're working on 5G test beds with OAI, SRS-RAN, and different test beds. And my question basically was like, what was the purpose that you did not try with the existing stacks of the 5G? Like there also you have something similar to that. You can use SDRs, you can transmit the signal, and you can synchronize the USRPs if you want. I mean, now there is another question into this question. Why did you need to synchronize the USRPs, and how did you do that? First question. And second, like, did you try any open source 5G testbeds or not?
Fantastic. When I was doing this work, those were not, to my knowledge, available. I did not know of them at that time. Now that I know them, and I have I have a 5G test bed in my lab, like the OAI box, that is fantastic. I'm running also, I have the OAI software stack, the SRS-RAN software stack, and they were great. I'm actively doing what you're asking about, right? I'm actively trying to implement things. I have one paper, there was recent Infocom paper 25, I think, where we show why it's challenging to do this in the 5G setting. And the key thing there is the 5G access point does not know ADIO information.
Okay.
Because ADIO information is based on timestamps generated by the sources. So 5G base stations could maybe estimate them, but they don't know it. They don't know the ADIO information, right? So what we did in this Infocom paper, we created a mechanism that tries to estimate ADIO information. So I'm going to use this paper to implement things in my testbed. This is something that I'm actively pursuing.
Okay, so I have some ideas. Maybe I can approach you later and discuss about this.
That'll be fun for sure.
Because what we were interesting to do the delay analysis in a 5G testbed. So for that, you need to synchronize your USRPs. We suffered actually a lot over there to just how to synchronize it in a 5G testbed. But I will not take the time of the meeting. Maybe I will approach you later to discuss. Thank you.
We can talk about synchronization then later too.
Yes, thanks.
Thanks, Arash. I guess there's a question from Shakil asking how can multi-armed bandit algorithms be adapted for real-time wireless resource allocation under channel uncertainty and latency constraints in millimeter wave with interference among agents? I think in probably the question, I guess there was you mentioned the 8 optimal in your slide, the multi-armed bandit question. Probably it's related to that.
Right. Yeah, we did not do millimeter wave. It was all like Wi-Fi frequencies, right?
Okay.
But to adapt our to use like multi-arm bandits, the first thing that we did was, in multi-arm bandits, at least in the stochastic one, you kind of assume that whenever you don't pull whenever you don't activate the agents, then its state does not change. But with age information, they change, right? Even if you don't activate a particular drone, the age information continues to increase. So we actually had to use the restless multi-arm bandit to get there. And one particular thing that I thought was interesting about the result is that usually when we prove performance guarantees for restless multi-arm bandits, we try to prove like asymptotically optimal results for like number of drones going to infinity. The 8 optimality that we got was for finite number of drones. So if you have like 3 drones, 4 drones, I'm not doing anything asymptotic, you get 8 optimality there.
I see.
But maybe the question is deeper. And Shakil, I'm happy to talk offline if you want
to. Yeah, I think that definitely tells some of the high level idea. Yeah, we can talk offline if needed. Thank you.
Happy to do that.
Okay. Marty, I guess Marty's question probably relates to, in a way, maybe partially answered by one of your slides about seeing, because typically it relates to the, I guess, packet generation, I believe.
Yeah.
Why is it multi-targeting? Yeah.
This question is fantastic. And this is the problem with Wi-Fi, right? With Wi-Fi, at some point, you're adding more and more nodes.
Yeah.
You have this first come, first served queue. You're adding packets. And as you're increasing the number of drones in your system, the transmission rate is reduced. The per drone transmission rate, effective transmission rate reduces. So at some point, the generation rate is going to be greater than the transmission rate, and your queue is going to blow up. With Wi-Fi, it doesn't happen because first, you have a less come, first served queue. So whenever you transmit, you transmit the freshest packets. So even if the queue is infinite, at the head of the line, you have the freshest packets. So there's no end star that things blow up. So in our system, age information degrades gracefully, but like linearly with N.
Yeah, so okay, looks like we have many questions coming. I guess there's a question about future research directions regarding AOI.
Yeah, this is something also related to what I was hinting at before, right? So when we have the 5G test bed, we have this fantastic software and hardware from OI Box and different vendors, NI, right? And we're thinking, can we implement, age information scheduling policies for 5G? And to my knowledge, this has not been done. There are some very interesting work that tries to go overcome the problem that I mentioned, that the 5G base station does not know age, to try to optimize something different that would kind of like help age. But to my knowledge, there's no implementation of a protocol in 5G that would minimize age. So I'm trying to do that right now in my lab. So I had again this Infocom paper, recent one, that deals with like estimation of age using the 5G cell tower, and then we're gonna implement that in the OAI and try to create a scheduler.
Great. Yeah, and then we have a question from Oluwasim. Probably the question is regarding the channel behavior. I think in the probably presentation, the discussion, we assume each link has a fixed PI.
Yeah.
I guess the question was asking if it's actually stochastic, whether and how we may consider historic channel behavior in the decision policies. How would that impact some of the result?
Yeah, that is a great point. What we did was kind of like what I mentioned. We estimate, so in theory, we assume P is fixed. In systems, we have to estimate P. But I think that the question is deeper, right? It's asking like, if you're in theory, you're assuming that this channel is stochastic, can you use history to kind of like predict channel and then, improve your scheduler? And I think, yes, it seems like an interesting, venue to explore.
Good,
I did not do that
study.
yet.
Yeah, good.
Very interesting.
And then Arag, the last question, so maybe Jay, you and I can alternate. I haven't get just read. Maybe Igor, you can answer.
Future potential.
Yeah, I think it's related to the earlier question about, is this field still ripe for other opportunities for new students? Yeah.
I think there's a lot of, there are thousands of papers on this already, which I'm not saying that it's closed and done, right? Even the simple problem that I consider is still an open problem. So if you can address that, that's going to be huge. Another aspect that I encourage you to take a look at is like implementation of these things. And this, like, you can definitely, if you don't have a test bed, you can use R to do that. or leverage R actually to do that. You know, implementing those. So we have so much rich theory, so many geniuses coming up like algorithms and proofs and bounds, but you know, not a lot of people are implementing those things and showing that they work in practice, right? So if you can do that, Bridge, that would be, you know, important, you know. So think about smart factories, right? I think the position certainty thing that I mentioned is also relevant there. You know, you have robots, they're moving, you have maybe robot arms, and their position is important to know, right? To my knowledge, there's no one implementing things in, you know, and showing that they work to address those important problems.
Right, right. If I may, I should put a shameless plug here. You know, I think since Igor mentioned ERA, one of our, you know, probably related to the question, I think in general, I think timing related questions, both theory and practice, remains to be one of ground jewel, holy grail for wireless systems in general, right? It was the interest was there in even 5G, but we didn't succeed. You know, remains to be one of the key driver for 6G. I think definitely this is where we do need a lot of brain power and people power. As part of the ERA effort, actually, we're thinking about, you know, kind of how we can kind of bring folks interested in certain topics together. I use ERA as a platform to building communities collaborating ways that probably not as easy as how it could be, right? I think especially when we want to bring theory and practice together. And just because we only have like 20 hours per day, I think there's that community engaged, you know, kind of, there's a question about how we can potentially collaborate in ways that we can probably uncover new problems, be able to tackle challenges we cannot tackle alone. So that would be actually one thing we would be interested in, be a broker maybe of some sort, since we're running the community test bed. Folks interested, you know, we would love to hear from you and how we can be of any help in making that connections through webinars or some other mechanisms. I know we already are over time, but Igor, if I may just share one question, and then just in case that may be of interest to the crowd here too. Just like many solutions, right? Especially when we look at many of the optimization problems, oftentimes we look at the asymptotic behavior. And in the meantime, I think that does actually have a lot of applications, right? In the meantime, especially in certain those safety critical applications, it's actually the short-term behavior that actually matter a lot. So I'm curious. Looks like it's been there's like 13 to 14 years of research by, as you mentioned, thousands of studies so far since the first paper came out. I'm curious where we are in terms of understanding how to design and reason about the distribution of AOI. Any like anyone actually focus on that thread of effort so far, and is that worthwhile to look at?
Yeah, you mentioned like distributed or like
distribution, right? Instead of looking at the, for example, in the problems talk about today, we look at the maximize the weighted AOI in the long term, right? Asymptotically. I guess I'm curious about, but AOI, if you look at it as a random variable, right? So even if it's stationary, the come on.
okay, we're back.
Sorry, was it just me?
No, I think it was me too.
Okay, did we lose everyone? Oh, okay. Okay, we still have everyone. Thanks. Sorry. So my question is the following, right? You see AOI, right? If you look at individual samples, it's a random variable, right? Any study about the distribution of the this random behavior? Because you know, whether it's really heavy tail versus that also matters quite a bit, right? In some applications.
Yeah, right. I know that if I remember correctly, there was some work in like minimizing like tail age information, right? Making sure that the
Okay.
probability of like very high age information is
Okay.
lower than some threshold, because exactly of what you said, right? In some, you know, like in a factory setting, maybe you don't care if age information is up to, I don't know, 2 seconds, maybe you don't care. But if it's beyond 0.5, you really care. So you don't really care about minimizing age, but you care about minimizing the tail age. So there were some works in that direction. But I don't know. Most of the works that I still read, like in the literature, even like the ones that I recently like reviewed, they still consider like expected age of information.
Right.
That's a very challenging problem. Even expected age is challenging.
Right, understood. Yeah.
But it's very interesting, because it's very relevant too, right?
I see. Hey,
And
if you
also-
know any such article, I'd love to hear from you some pointers.
I can share. And Hongwei, I also remember there was a survey. You were talking about building community. There was a survey that you sent, right? As part of RFest, I think.
Oh yes, as part of that, yes, we did.
Yeah. So maybe you could. I think I already fill it in. But
Yes, we need to study that, and we'll probably get back to the community too. Thanks for sharing that, actually.
Yeah.
All
Fantastic
right.
idea.
Thanks for folks for staying with us for over like 13 minutes already. I guess I think Professor Igor's email was there. I think if you don't know, Google his name, you can find him. But if not, feel free to reach out to me, and I'll be happy to share, connect. All right, thanks everyone for joining us, and thanks Igor for this wonderful talk. We can enter. There's a small room. We can have just looks like we have about 30 minutes. We can go there. All right, see you.
That's fantastic.
All right,
Thanks for the
thanks
invitation.
everyone.
Thank
Take
you.
care.
Bye-bye.
Bye.